those problems. So I'm going to do it right now. Turn on my camera. I'm going to do those chapter 7 problems for you guys. And then I'm going to keep this video so that I can share it with my other class as well. Let's look at number 9 in section 7.1. This is actually a nice problem as well to understanding. So now I'm moving back into the eigenvalue, eigenvector material. Let's take a transformation T that goes from R2 to R2. And of course, that's going to be represented using a matrix. So here's my 2 by 2 matrix, right? And what it says here, I'm going to read these words, but then I'm going to show it to you mathematically. It says the effect of A as a matrix transformation, the effect of A is to flip every vector across the line y equals x. Let me see if I can convince you of that. I'm going to draw the xy plane. And I'm just going to draw the line y equals x, which would be roughly going at a 45-degree angle like so. Okay, so this is a geometry problem. This is really this problem. I put it in here to have you remember the importance of the geometry behind eigenvalues and eigenvectors. So let's just say that I picked a vector here. I'm going to pick the vector, I'll just pick 5, 1, just to make something up. Right? Now, if I was to apply this transformation to 5, 1, how would I do it? I would take my matrix, like the way that, remember, the way this works, guys, is you just do A times X. T of X equals A times X. So I would take my matrix A here, and I would multiply it by 5, 1, right? And if you actually were to do that, if you calculate that out, just check how the matrix multiplication comes out, you should end up getting 1 and 5. You see that? And so where is 1, 5 on my graph here? Let's see if I can just draw it with a different color. So 1, 5 would be like up this way somewhere. 1, 5. Well, that's what these words are saying. The effect of A is to flip each vector across the line y equals x. Do you see that? This blue vector, you kind of flip it across that diagonal dotted line. Okay. You with me? So I could pick anything. I could pick, just to maybe do one more example. If I picked, let's pick the point 8, 2. Right, so 8, 2 is probably, over here somewhere, right? There's 8, 2. If I flip that across this dotted line, it's going to end up, up here somewhere, 2, 8. And as I calculate this, that's exactly what happens, right? And what they're asking us to figure out now is to find all of the eigenvalues and eigenvectors. But I want to do it without using the characteristic equation and doing the whole null space thing. The stuff we were doing earlier, I don't want to use that. I want to do it from thinking about the concept of it. Is 5, 1 going to be an eigenvector of this matrix A? Just going to remind you that anything that is an eigenvector should just simply be stretched. It should not turn. It should not start pointing in a different direction. It should just only be stretched. Is this vector 5, 1, when I apply the t to it, does it just get stretched? No, it gets turned, right? This vector here, right, it turns like that. It's not looking like that picture there. Same thing with 8, 2. If I start with 8, 2, and I flip it across the line y equals x, it's not pointing in the same direction anymore. The question is there somewhere that you could draw a vector to start with on this picture that would not change directions when you did this flipping across the line y equals x? I see some ideas here. Chris, I think I saw you first.
It would be perfect.
Oh, what if my vector was directly to begin with, right? If my vector is directly on the line to begin with, and then I'm flipping across that line, where does the vector go? well, let's just pick a specific one just to kind of visualize the math of it. Let's say I pick the vector 3, 3. That would be right on that dotted line. What happens when I do this calculation? 3, 3.
3.
Where did the vector go? Nowhere. It stayed exactly in the same spot. In other words, in that case, A times V was equal to V. So that is a good point. So the answer, now I'm going to start doing the solution here. Any vector of the form, let's just say A comma A. So it doesn't have to be 3, 3. It could be 5, 5, or 9, 9, or whatever. Is an eigenvector. And my question then would be, what would be the lambda value? So remember that the lambda value is how much is it getting stretched by. So if I take this vector that's right on that dotted line and it just sits there, then what's the lambda value? Jesse?
1.
It's just 1. Yeah, it's just 1. It's just 1. It's just lambda equals 1. That's exactly right. So any vector that's directly on the line would be an eigenvector. And you can see the 1 is right here, right? You just put a 1 right there, right? And so the scalar, the lambda value is just 1. Okay, that looks good to me. I do expect, however, to probably have 2 different lambda. Well, think about our fun facts. Ooh, oh, that's going to give away the answer. So if one of my eigenvalues is 1, and it's a 2 by 2 matrix, what's the trace here? Trace is just 0. So what does my other eigenvalue have to be? -1, right? And so that would be an what does the eigenvalue -1 do? It takes this vector that's pointing this way, and it just flips it 180 degrees the other way. Can we see where that vector would be on this picture? What would be a vector that literally just gets flipped 180 degrees? If I started, say, right here, for example, that's a 90-degree angle with the dotted line. And then if I flip it across that dotted line, that blue vector would then become my, that would then become my image vector. I'll do it in green here, pointing that way, if you flipped it across that line. So I'm just going to add another sentence here to mention that part of it. So any vector of the form. Oh, what would be the form of this, by the way? This vector that's going at a 45-degree angle down into this 4th quadrant, what would those points look like? You know, it's not going to be A comma A anymore. Oh. One more time.
A comma negative A.
Yeah, exactly. That's going to be A comma negative A, right? So like this vector might be the vector, I don't know, 2, -2, for example. Right? And that is also an eigenvector. But this time with lambda equals -1. Exactly right. So we have 2 different eigenspaces. One eigenspace is literally just the line y equals x. That's the first one, right? Anything of the form A comma A, that's just on the line y equals x. And the other eigenspace is exactly the line, this is actually the line y equals -x. The second component is the negative of the first component. Yeah, so that's the solution to number 9. It's, of course you could do it. You know, you guys could all do the determinant of what you get when, you know, you could subtract 1 from the main diagonal. Do your little 2 by 2 determinant. Okay, lambda squared -1 equals 0. Then you can solve for your lambdas and do your null spaces again. But the point of this exercise was to go back and remember the geometric interpretation of the theory of eigenvalues and eigenvectors. Okay.
So that's the answer for
That's
number.
the answer.
So we show it. I show it first, then we write the.
Right. Guys, do I have 1 minute to show you 42B? Could I do that?
Do you want to?
I do.
Okay, go ahead.
Is that okay with everybody?
Sure.
You're speaking for everybody. I just want to, I can do 42B in like literally 30 seconds.
Are you serious?
I am. So 42 42 is just very simple. It just says if you have an eigenvector V corresponding to the matrix A with eigenvalue lambda, and then V is also an eigenvector of another matrix B with a different eigenvalue mu. So if this is given, okay, this will be really fast. It just says prove that V is an eigenvector of A plus B. Just to prove that. Okay, so this is very quick. I just want to show you how this works. If I want to prove that V is an eigenvector of A plus B, I just have to show it. This is a one-line solution. I just have to take the matrix A plus B. I'm going to apply it to V. And you simply just FOIL this out. So this is just, or you just distribute it, I should say. AV plus BV. And then you just sub in what was given here. AV is just lambda V, and BV is just mu V. This mu is just like a U with a long tail on the front of it.
Oh,
And then I'm going to factor the V out of the right-hand side. So if you just factor it, guys, the most important equation in chapter 7 is just this one, AV equals lambda V. So that's what I just did here, except with A plus B. A plus B times V is equal to lambda plus mu times V. Here's your eigenvalue right there. The eigenvalue is just lambda plus mu. It's a little theoretical problem that just takes only that amount of work to write it down. Okay, I just wanted to show that to you because I do like people to be able to use this very importantly. Thanks for the extra minute. If it was too fast at the end here, I can show it to you again in my office hours.